This series focuses on data structures and algorithms content, and in this recording in particular I will talk the third part 3 of the bubble sort algorithm subseries, analysis of this algorithm. We can see complexity of an algorithm from the perspective of the amount of time required and the amount of memory space required when the algorithm runs. These are called time complexity and space complexity respectively. Talking about the space complexity for bubble sort algorithm, this is the code that I came up with in the previous part 2 recording of this subseries. We can see this function merely requires local memory space, which is actually the extra memory space required by the algorithm to perform the sorting task. Memory space required for the variable called temp, local variable temp, and that required for the iteration indices I and B used in outer loop and inner loop, and also there could be some temporary memory space required while evaluating the expression that are placed in the conditions for the for loop and if structure. These are the memory space that are required by this algorithm. So extra space required does not grow with the size of the data, that means the length of the array that is passed into it or the value of the size parameter variable. It remains same regardless of the size of the data received by the function. Therefore, the space complexity of a bubble sort algorithm is big O1. It is also called as a constant space complexity. Now let us look at the time complexity at a very high level or at a coarse level. The coarse level analysis focuses on how the algorithm scales with data size, and this analysis is not concerned with the precise or fine-grained counts of the operations that are involved. For this purpose, we consider both the comparison and swapping as a tightly coupled unit, and we also consider this as a unit that dominates the time complexity in one iteration of the inner loop. Here we use the term one pass to refer to the entire run of the inner loop from start to finish, completing execution of the all the iterations of the inner loop. In the first pass of the inner loop, this loop executes with a value of I equals to 0. This is a value that is received from the external loop or outer loop. When this inner loop completes all its runs, the computational unit of the comparison and swapping is executed for a total size minus 1 number of times. Therefore, the time complexity for the first pass is size minus 1. Again, this inner loop actually has total size minus 1 iteration, because in the condition on the right side of the comparison, in the condition the expression is size minus I minus 1 and the value of I is 0. Therefore, it is size minus 1, which indicates that this loop actually runs for size minus 1 number of iterations. Therefore, total number of times for which this computational unit is executed is size minus 1. Therefore, complexity for the first pass is size minus 1. In the second pass, we have I equals to 1, again coming from the external loop, outer loop, and the computational unit runs for total size minus 2 number of times, which means size, if I is the value of I is 1, then this expression size minus I minus 1 will be size minus 1, which is size minus 2. So computations for the second pass is size minus 2, and for the third pass with I equals to 2, the computation is size minus 3. In the fourth, fifth and sixth passes, the computation is going to be size minus 4, size minus 5 and size minus 6 times. computational unit is executed for that many number of times. And in the second last pass, where the value of I is size minus 3, this computational unit actually runs for 2 times. So if you evaluate this expression on the right side of the comparison, size minus I minus 1 with I equals to size minus 3, you will have it 2. So it will run for 2 times. And in the final pass with I equals to size minus 2, it runs for 1 time. So the total cost can be obtained by adding all the computation numbers in all the passes. So size minus 1 plus size minus 2 plus size minus 3 plus dot 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 plus 3 plus 2 plus 1. So this is actually the addition of the integer numbers starting from 1 to the largest number, size minus 1. And we have a formula to compute the summation of this expression, total sum, which is shown in the right side, n plus 1 by 2 divided by 2. And in our case, size minus 1, if we use lowercase n, smaller n, to represent the size, then our expression will be n minus 1 times n divided by 2, and if you expand that, it will become n square divided by 2 minus n by 2. So in this case, the dominating term in the expression n square by 2 minus n minus 2, or highest power term, is n square divided by 2. Therefore, big O complexity of the bubble sort is big O n square, or quadratic time complexity. Finally, I need to mention that worst case complexity, what we discussed before, this is the worst case, because we assume that computational unit will be executed for all the iterations of inner and external loop. That happens in the worst case. But sometimes there could be no need for sorting, or sometimes it is possible that we can terminate after only one pass. So in the best case situation that comes when we have already sorted array passed into the algorithm, so there is no need to swap in any cases. In that case, we can we can make a small change in the program, so that the program actually, this algorithm actually terminates, or external loop terminates only after one pass. So amount of computation required in one pass will be big O n. Now in the average case, it comes when you have an array where we have partially sorted, partially not sorted cases, 50% sorted, 50% not sorted. In that case, approximately half of the time the inner loop, the swapping is to be conducted for half number of times, half of the maximum possible number of times. So in that case, it would be something like n plus 1 divided by 2 complexity. So even in that case, as also the dominating term will be n square. So the complexity is big O n square. In the worst case is the case we discussed, in which if you pass an array which is reverse sort. For example, if I want to sort in ascending order, but the array that is passed is in the descending order, in that case you have to invoke that swapping process in all the cases, so which will actually require computation in all the loops of external and inner. And as we showed in the previous computation, it is big O n square. So we can also call this as the worst case complexity is upper bounded by big O n square. Average case complexity is upper bounded by big O n square, and the best case complexity is upper bounded by big O n. This is all I have to talk about this topic. Thank you for watching this video.